Alright, we'll find out later. Right, so those pages which are effectively just an array of record slots, how do we manipulate them? Or how do we add things in and delete them? So let's have a look. Here's an attempt. No, it's actually a .c file, not SQL file. Okay, so we can imagine that there are some data types like byte and count. And this, by the way, this is never going to work in C because there's a whole lot of type mismatches and things like that. But just to get the idea. So we could have in our page, and remember that in the diagram on the slide, it had at the bottom of the page a counter. Okay, so we're actually going to go in the reverse order. We put n at the top, and then we're going to work down from there. But so we need a counter for the number of records. We also need to know the total number of records. Now, if we actually had a record size stored somewhere, and eventually we need that, maybe we could store that there as a replacement for maximum number of records. But we need to know if the page is full. And it might help if I turned on the microphones. All right. The dirty little trick that we're doing here that Postgres does a lot is this one. So it looks like we're saying that our data is a single record, but all we're really using this for is to get this offset in the struct. And we actually have all the other records just follow on from that, but they're just not mentioned here. So Postgres does this quite a lot when it can't be bothered working out the size of an array. It just gives the first element at the end of a struct, and then the struct just expands to as big as it needs to be. So while it says 1 here, it's actually the total number of records in the page, which could be something like that.
Sorry, is that so are you saying that's a linked list, or are you saying it's something really weird for every application?
Yeah, it's all it does, I mean, a struct basically tells you, gives you a list of field names, and each field is associated with an offset. So nrex is going to be stored at the start of the struct, offset 0. Then this will be stored after nrex, and if count happens to be a 2-byte value like it claims here, then that would be at offset 2, and then data would start at offset 4. And what Postgres does a lot is it defines a struct like this, but it actually allocates a big chunk of data and sort of uses this as the starting part of the data, and then just pretends that there are as many elements as we need, as many record items as will fit in a big chunk of data. So I'm not sure that I've used it 100% the way that Postgres does. I might try and fix that live, but in any case, how do we initialize it? Maxrex, nrex, well obviously nrex is initially 0. How many records can we store in the database? Well, we have to take account of these two things which are stuck at the start of the page, and then the rest can be used for data. So maximum records total page size minus the size of this object, which it looks a bit funny. Maybe I should have called it page header or something, because that's really what it is. In any case, so, and notice that we're always dealing with it as a pointer. So the size of that struct, the page header at the start, plus we've got to allow 1 because the size of the struct includes this, which includes a single record. So that's actually one of the records that we can store. And then we divide all that by the size of the record to get the number of records that we can store. approximately like that, but basically it's the size of the page minus the header information. Right, adding a new record into the page. Now remember, we assume that the page contains the header plus record slot, record slot, record slot, record slot, all the way up. Once we've run out, once we've used all the records, once we've seen NREX records, then the rest of the page is free space. So if we want to insert a new record into the page, first thing to check, is there room? If there's not, then we've got to fail somehow and say can't fill up. Now of course in a real database you're never going to do that. There'll be some way of getting around this, maybe an overflow page, something like that. In any case you can't insert the record directly. Right, then we need to work out whereabouts in the page are we going to insert the new record, and the new record is going to be the next free slot. So NREX, when NREX is equal to 0, means we've got no records in the page, and if we take the address of pdata 0, that's going to give us the first record slot, the address of the first record slot. So we get that address, we've got a pointer to a record, and we do a mem copy, and obviously we need to sort out the types here, and we copy the size of the record. Okay, so record is a fixed size object in this context. The insert function, we need to return the index of the new record, so we just grab NREX, and then we increment NREX, and then we return the index of the element of the record that we just added. So, okay, reasonably straightforward, as long as the page isn't full. When we come to delete a record, we have a problem. Now remember that a tuple ID or a record ID consists of page ID and an offset within the page, which is actually an index, or generally it's an index. Now in this context, the index corresponds to an offset. So records are identified by which slot they occupy, and that information may be propagated to various parts of the system. Now, if we want to delete a record, we always want to have a single region of free space at the top. So if we take a record out of the middle, we need to somehow make sure we don't leave a gap in the middle. So the easiest thing to do is to take the top record and move it down, which is what this code is doing. But by doing that, we've actually changed the tuple ID of the record that we just moved. So that is a problem. Or the record ID, tuple ID, same thing. Plenty of other page strategies get around this by having a dictionary which tells you in which the records always occupy the same slot in the dictionary, but you can move them around because the dictionary entries say where the record actually exists in the page. So this very simple structure here isn't going to work, basically, because you're changing the identity of a record to maintain that packed free space area. Alright, so let's have a look at how we really do it. So right, so now what we have is we go back to our diagram. We've got this scenario here. So we've got an array of bits, as many bits as we need to store records, as many records as we can fit in the page. And then we've got the record slots themselves. So when we delete a record, we don't even have to do anything up here. All we need to do is reset the value down here to 0, which tells the system there's not a record there anymore. Alright, so how does that change things? Well, one problem with this is we need to know up front what the maximum number of records is, but that's determined by the record size. And while it would be nice to do bit present 1, so we can make the presence array as long as we liked, and we can make the data array as long as we like, unfortunately you can't have 2 of these little tricks in the same struct. So everything up before the last one has to be a fixed size. So I just made up some number here, maximum number of records could be 100, and this, remember, this is an array of bits. So up front we have to make a decision as to how big we want that presence array to be. And then we use the same trick as before, we just have a labeled data, which is an offset into the page, and then everything that follows is a slot. Alright, how do we initialize the page data? Well, all we need to do, there's no tuples, we don't have a tuple, a count of the number of tuples, we simply set all of the presence bits to 0. Inserting a tuple, a new tuple into the page, first of all, we need to find a free record slot. Now, maybe there isn't one, in which case we got a problem. But all we got to do is scan through the array of presence bits, and as soon as we find a 0 bit, we know we can use that slot because there's nothing currently there. So we iterate through all the present bits. As soon as we find one at 0, we remember where we were and we break out of the loop. We initialize slot to -1 just so we can detect the fact that we didn't find a free slot. If we did find a free slot, then that's where it is. Slot is the index of where we're going to insert the new record. So we work out its location, its address within the page in terms of a memory address. We then copy the contents of the record into the location, then we return the slot where it was inserted. So that's all very nice. It's not much more complicated than the other one, but it's when we come to delete that we see that it works quite nicely. So to delete something, we simply set its presence bit to 0. When we're doing a delete, remember that the arguments that we give is pointed to the page structure and an index into the page. So we simply use that index as an index to the present bits, and we're done. So that's a reasonable way of implementing fixed size records. Alright, for variable length records, as I mentioned before, we don't just store tuples in the page, we need to store other stuff that tells us whereabouts tuples live and other kinds of information about each tuple. For example, its length, because they're variable length, we need to know how long they are. So, once again, we could have a compacted here, because we're using a directory, you can see that it's easily possible that we can move tuples around and it doesn't affect their tuple ID. So if we wanted to, we could have a compacted free space, which means all the free space is in one contiguous region and all the tuples are sitting somewhere else, or we can just let the whole page fragment, which may not be such a great idea in the long run, but in practice, what's a useful thing to do is to allow page fragmentation, but every so often do a compaction step that pushes all of the tuples down to the bottom of the page or the top of the page, depending on which order you're doing things in, and then has all of the free space in a single chunk. So, as I said, the killer about using a slot directory is we can move the tuple around and we don't change its ID. Its ID is always an index into this table here. So here's an example of compacted free space, which isn't quite realistic because it looks like there's only 3 records floating around in this region up here, but in fact this region is full of records. There's no free space up here. All of the free space is down here. And so what do we need in a thing like this? We need to know how many entries we've got in this, so we need to know that end value there. We need to know where the free space is, so when we come to insert a new tuple, we can always stick it just there and add a new entry on the end and make it point to where that used to be. And what else? Oh, that's about all. Yeah, counter, and each of the entries in this array tells us the offset within the block where this record starts. And potentially we could add other information as well.
So it is storing the pointer, or?
Yeah. So this array down here just contains pointers, or it contains structures, and one of the components is it's not actually a pointer, it's an offset within the page, and then we can compute a pointer value if we know where the page starts plus the offset. So, but yeah, the critical thing is that this record 2 is always going to be accessed from here, regardless of whereabouts it's located on the page. And if we're happy to allow fragmented free space, then we can, once again, we've got these free and record slots sort of floating in a sea of emptiness, but in fact all of this is full of records. So we've got our directory which points to each of the individual records, tells us whereabouts they're located. We've got a pointer to the first chunk of free space, and that's going to a pointer and offset, and then that's going to have a reference to the next chunk of free space and a reference to the next chunk of free space, and so on. Alright, so if we want to insert a new record, well, what we do is we need to find a place to insert it. So we go to the free space list, we look at this chunk of free space. Does the record fit in there? No, it doesn't. Look at the next chunk. Well, if it didn't fit in there, it probably doesn't fit in here either. Look at the next chunk of free space. Yes, the record fits in here. It might occupy that part of the free chunk. So we put the record there, and then we rearrange this pointer here to point to the start of the real chunk of free space that's left after the new record that we added. And we need to add an extra entry into our directory to point to the place where we just added the new record. So that's all very nice until we end up with a large number of these small free chunks, and in total they might add up to a large amount of space, but if you're trying to insert a record, it doesn't fit in any of them. So we imagine that free 3 isn't really there. We've got free 1, free 2, free 3, free 4, free 5, and they're all quite small. So that's the point where you're trying to do an insert, you realise that there's no free chunk that it will fit into, but there are a large number of free chunks, so you rearrange the location of all the objects in the page, and you're free to do that, so you can easily move record 1 up to there, record 2 to there, record 3, blah blah blah, record n, and then have all the free space down here again. So that's the way you deal with that. So here's another example. So the page initially starts out like this. So there are no records. and therefore no directory, and the free space is located up here. So here we're going to imagine that we start adding records from the top of the page and add them down towards the directory and the other header information. So if we inserted 6 records, they might look like that. So we've got 6 records. R1 is the offset of record 1, which is going to be 1023. Sounds like a bit of a strange offset, but R2 will be the offset of this record, R3 will be the offset of this record, R4 that one, R5 and so on. So if we come to insert a new record, then all we got to do is look at this value. We can see how much free space is available there. That's pretty straightforward because it's going to be all the way from 719 down to the end of this array. And if that amount of free space is big enough to hold our tuple, we can put it there, add a new entry onto the free array and end up with something like that. Okay. Now, of course, you can see there's a potential problem brewing here, that if we add more and more records, then this grows larger and larger, and eventually they may collide. So once again, we've filled up the page. What can we do? Some kind of overflow page or some other structure to deal with that. So if we're dealing with fragmented free space, that was the initial state, same initial state, we might end up with a scenario like this by the time we come to insert our 7th record. Why might we get that scenario? Or maybe we used to have a record there and we deleted it. Maybe we used to have a record there and we deleted it. So we know where the first chunk of free space is, and at the end of this chunk there's going to be something that tells us where this chunk is, and so on and so on. Right, so we come to insert the new tuple. So we're first of all going to go up to here and say, does the tuple fit in here? If it does, then we're done. So we grab as much of that free chunk as we need, and the remainder of that free chunk becomes the first entry in the free space list, would be the easiest way to do that. So after inserting record 7, we decided that record 7 was going to go down here, in fact, for some unknown reason. But in any case, we've added record 7 down here. We've added a new entry for record 7 in the directory, and that should be 7, because now we've got 7 records. The free space list still hasn't changed because we're still starting from this chunk. You might wonder, why didn't record 7 end up in free 3? Well, potentially it could have, but maybe the free list isn't ordered in exactly the way it looks like that. Another thing you can see is that we've ended up with a small chunk down here, which is eventually going to be filled up with the directory, and is also probably not going to be useful for storing any records. What's time? All right, I won't bother with that. We could re-implement the insert functions for a scenario like that. Obviously, it's going to be more complex than the simple record slot style that we had before, because you've got to manage all the free space lists and the directory. Alright, so one thing that might have become clear from looking at that, how many records can we actually fit on a page, given that we've got some overhead with directory and header information, and we may have chunks of free space floating around. So that depends. How big is a page? That's the first thing. How big is a record? Well, if we know if records are fixed size, we can easily compute the number of records. If they're variable size, then it becomes a little bit more difficult. So we could consider something like that, an average record size. Page header data, typically a few bytes. and the slot directory, the size of the slot directory depends on how many records we've inserted. So to work out, well, if we know our capacity, then, well, if we want to work out our capacity, we've got to solve this. And so the size of the header, the size of the directory, and the size of the current records that are in the page. And all of that has to be less than the page size. So you can sit down and we know all the values except C, so we could work out what C could be, the maximum number of values, the maximum number of entries. All right, so here's an example. So imagine we've got 1024 byte pages. We've got records that look like this. Notice their variable size because they've got varchars in them. They have to be aligned on 4 byte boundaries. The C field, is padded, okay. Yeah, so interesting aspect of things like this is if I was allocating records like this and I put just 10 chars, then, and the next field is an int, then it's not aligned appropriately. So what I'll need to do is pad that up to multiple of 4 so that the integer can be set. So the C field has to be padded. Each record has 4 field offsets at the start of the record. That's something we haven't talked about yet, but when we talk about tuples, we'll see that. The maximum size of a B value is obviously 20 bytes. Let's say the average is 16. Page has got 32 bytes of header information starting at byte 0. So, how many tuples can we add into this page? So, let's see. I really need to have all this information in front of me. And I've probably got it already. Maybe I do. Yeah, okay. So here's the working out. So the header starts there in 32 bytes. There's a directory. The entire size of the directory starts from 32, goes to 32 plus C, at which point the free space starts, goes up to a certain level, and the records are coming down from the top of the page. So to work out the size, the average size of a record, 4 bytes, 16 bytes, because we were told that's the average length. The C attribute, 10 bytes plus 2 bytes padding, so that gives us the average record size of 40 bytes plus, sorry, that wouldn't add up to 40, that would be 20, 32, 36, plus we need some stuff at the front of the tuple to tell us where the field values actually start because they're variable length. So otherwise, how are we going to know? I really should have jumped forward and quickly had a look at it's jumping a long way forward. Oh well, I won't jump forward. No, I will. Where is it? Variable length records. Okay, so the kind of thing I'm talking about is something like this. So we need to know, we've got this field starts at a certain location. This field, variable length field, starts here. We know that for sure, but it could be arbitrarily long. Similarly for that, if we're doing it as a string. So at the start of the record, forget about this stuff. Imagine that we've got 4 of those values that tell us where the attribute values actually start within the chunk of bytes that makes up the record. So average record size 40 bytes. Alright, so B is the total page size. B is 1024, and these values that I'm using here are going to be values that recur frequently. So B is the total block size for a particular database. R is going to be the average record size. Lowercase r will be the number of records. Lowercase b will be the number of blocks, and so on and so on. So the amount of actual free space that we start with before we insert any records into the page is 992 bytes. So if we've got n records in the page, we lose 1 byte of free space for each record that we've added, and the records themselves are that big. So if you work it all out, it turns out that you can store 24 records in that 1024 byte page. So a value like this is not atypical, although Postgres has 8K pages, but certainly dozens or hundreds of tuples in a particular page would be typical. It's a long way ahead. Where are we? Alright, so something I've alluded to a couple of times already. If you can't fit a tuple into a page because there's not enough free space, that's not likely to be a problem, because if you've got fragmented free space, you can easily, as you're traversing the free list trying to find a chunk of free space that's big enough, you can add up the size of all the chunks. And if the size of all the chunks is larger than the size of the record you're trying to insert, clearly you could compact everything and make a big enough chunk of free space to fit the record in. So that's not necessarily a problem. That would be a problem. So you traverse the free list and discover there's scattered through the page, there's 200 bytes of free space. The record that you're trying to insert is 256 bytes. Clearly it's not going to fit. And of course it's kind of obvious that it won't fit if the record is larger than 1024 bytes, if that's our page size. And also if the directory has met the tuples, then we can't add any more tuples to the page. So, as I said, you can fix case 1, but if you can't fit the tuple into the page, then how do you handle it? It depends. So, if we've got a file and we don't care where the records go, then we can simply add a new page on the end of the file, or we can stick the new record in there. It doesn't matter. So, make a new page. If we've got a case where the page that the record goes into is determined by something like a hash function, then it has to go into that page. There's no room in that page, so what we do, we add another page somewhere else and we link that base page to the overflow page. In the case where we've got a giant record, or at least a giant attribute in a record, so it's not going to fit, we can create an overflow file and stick the value of the giant attribute there and have a reference from the tuple into that. So that's the toast solution.
Can we also compress the data itself?
Or you could try that, yeah. That might be a valid thing to do, but you know, even if you compress it, it might still be too big. So then you end up with one of these solutions. So here's an example, or two examples. So here's a base page in the data file, so in the 0th fork, if you want to talk about it in Postgres terms, which has a number of records. One of these records doesn't fit, so we put it in an overflow file, and what we have here is something that says, hey, this record isn't really here, it's somewhere else. So using the offset, we can go and find it. If there's only a single overflow file, that's fine, and you can, that's something that's sort of feasible. So whereabouts in the overflow file does it live, and how long is it, might be a useful thing to know at this point. So that would be one way of handling it. And since Postgres deals with blobs, which are basically large chunks of binary data, you know, if you want to store images in the database, things like that, then this would be a typical structure for those kind of things. So you can store all of the image data here, and in the base page you simply have a reference to that. Now here I've said you could store the entire large record, but equally well you could store most of the record structure, but the particular attribute value for the attribute that's too large could be stored in the overflow file. The rest of the record might appear here. If we're dealing with not large chunks of data, but we're actually dealing with too many records trying to fit into a page, then we might want to have a secondary page which contains records as well. And so in the primary page we'd have some kind of tag. I just made up the tag FF, but some kind of tag that indicates the record's not really here, it's elsewhere, and we could use a record ID to indicate whereabouts it was in the overflow page. Alright, so what does Postgres do to represent all this stuff? Is that a hint? I don't know. There's people trying to break in there 10 minutes early. So if you want to find out how Postgres represents pages, that's where you can find the information. So this is the code, and this is the definitions. So by default, each page is 8K. It's got a header which contains free space pointers, the kind of things that we saw on some of those diagrams before. It's got an array of entries which tell for each tuple where it is and how long it is, plus some additional information that we'll see on a later slide. There's a free space region, so it actually keeps things compacted, so a big free space region and the tuples floating around. Now the thing with deleted tuples in Postgres is that we don't actually delete them because of multi-version concurrency control. We simply mark them, so they don't actually go away until you do a vacuum, at which point you can then compress everything to have a single free space region once again. So take out the dead tuples and fix up the fragmentation. Obviously we've got to have the actual tuples, plus maybe there's a bit of space for some kind of indexing data or whatever. Large data items are stored in separate files. You don't actually see that from most levels of the system. It would occur at definitely at the file manager and the buffer manager level. Possibly the tuple management level would see that as well. And Postgres has something that is a little bit like SQL standard blobs. So things that end up in the toast file, they just go there and you don't have any say over them. Blobs, you explicitly say, hey, I've got this giant object that I need to store, I'm going to store it in a blob. So that's the difference. So here's what a Postgres page looks like. Got the page header, got the directory, got the free space region, which is indicated, the range of which is indicated by these two offset values. Then we got all the tuples stuck in here, and potentially some extra space used at the top. Right, so a page is simply a reference to the buffer in the buffer pool. And if you're talking about offsets within the page, that you don't need as many bits to do that. In fact, if you think about 8K pages, how many bits does it take to address all of the bytes in an 8K page? Shouldn't have asked because I don't know the answer. Might be 14 bits. Let's just check. Out by 1. Alright, 2 to the 13. So 13 bits will allow you to address all the individual bytes in the page. That's not really a helpful size, is it? Because it's not. Anyway, that's certainly enough to address a single page. In fact, it's exactly how much we need. If we need 13 bits, then, and we want to deal with things in terms of multiples of bytes, then 16 bits would be the next thing up. Anyway, the entries in the tuple directory contain this stuff. So they've got the offset, which actually uses 15 bits. That's fine, it's more than 13, as long as we don't put ones in the top 2 bits, otherwise we could be in trouble. The directory also contains some information about the status of the tuple, whether it's regular or whether it's currently that slot is unused, or whether it's a tuple that lives somewhere else, which is what that redirect is all about. So in some sense, the LP flags that we've got here kind of takes the place of where I wrote FF in the tag information inside the tuple and the length of the tuple. Now both of these 15 bits are too big for what we need, but at least they're not too small. So page header data looks like this. We saw PD lower and PD upper on the diagram. Where does the free space region start? Where does the special space start? A lot of Postgres data structures, particularly stuff stored on the disk, are tagged with a database version, because when you go from version 9 to version 10, they might slightly tweak the way things are stored on disk. And so you want a Postgres server to be able to recognize, hey, this is a page that is using an old version of the data structure, so I'm not going to try and interpret what I see in this page. What happens if you've got a database from version 9 and then you install a version 10 server? How can you move the data from one to the other? It's dead easy. You just do a dump while you've got the version 9 server running, install a version 10 server, start it up, and then create the database new and reload it from the dump. And it'll create it with the new data structures. Alright, that's close enough to time. Let's stop there and I'll continue this on Thursday.